So in this nuclear model of the atom, we have this nucleus in the middle. That nucleus represents virtually all of the mass of the atom and virtually none of the space, the volume of the atom. And then you've got this electron cloud around the nucleus that represents virtually all of the volume of the atom, but none of its mass. So you've got this weird kind of dichotomy in that nuclear model. You've got high density, low volume in the nucleus, and you've got all the volume you could want and virtually no mass in the electrons. And yet these two are representing the entirety of what we call an atom. So let's look at this a little bit more closely. From a relative size perspective, from a mass perspective, you get the differences of mass between a proton and an electron as being roughly the difference in mass between a baseball and a grain of rice. The baseball representing the mass of the proton, the grain of rice representing the mass of the electron. Overall, there's about a 2,000-fold difference between the two. The actual number is like 1,820 or something, give or take. But we're talking about a massive difference in scale here. As far as electrical charges are concerned, with protons and electrons, we have this duplicity, this equal but opposite kind of relationship. Electrons have a charge that is negative, 1.6 times 10 to the negative 19th coulombs. Protons have a charge that is positive, 1.6 times 10 to the negative 19th coulombs. Now, here's the thing. We rarely talk about the charge of a proton or the charge of an electron in terms of actual units of charge. So the coulomb, capital C, that is the official unit of charge. But we don't use it. The reason we don't use it is because on a scale of charge, protons and electrons don't have much. Again, we're talking 10 to the negative 19 in terms of the overall value of the charge. So we don't talk about protons and electrons in terms of their actual electrical charges. We talk about them more in what we call relative charge. So that unit, 1.6 times 10 to the negative 19th, we're going to call that a single charge inside of the atom. And if it's a proton, we know that that charge is positively charged. So we say that the charge on a proton is +1. And for electrons, we know that that charge is the same exact value, but of a negative quality. So we say that it has a -1 charge. And so long as we have equal numbers of protons and electrons inside of our atom, we call that atom neutral. It's electrically neutral, meaning it has no extra positives, no extra negatives. Now, we'll talk about what happens when that isn't the case, when we have extra protons or extra electrons. Those get into a different category of atoms that we call ions. But let's focus on the neutral atom for right now. And in the neutral atom, equal amounts of each. Let's talk about interactions. You might have heard it said at one point in time in your life that opposites attract, and that is definitely true when it comes to electrical charges. Positively charged items will attract negatively charged items. They'll come together. But if I have like charges of either kind, positive and positive, or negative and negative, they are going to repel each other. They're going to push each other apart rather than attract. So one of the things that holds an atom together is the fact that you've got these attractive forces that exist between the nucleus, which is positively charged, and the electron cloud, which is negatively charged. And that attraction is what keeps that atom together. And ultimately, it is going to happen in such a way that it's going to largely negate these other forces that exist. Because you might also be thinking to yourself, well, wait a second, if positive forces repel, why is there a nucleus? You got all that proton packed into that really tiny space. Why doesn't it just fall apart? Well, there's a couple of reasons. One of them is something called strong nuclear force, which is well beyond the scope of this course. The other is that you've got attractive forces between the protons and the electrons that are generally overcoming the repulsive forces that exist as well. We can summarize what we call the subatomic particles. That is the protons, neutrons, electrons, the things that make up an atom. We can summarize them with this table. And to this table, I would actually add one more thing. So when it comes to these masses, you can see that we have the mass of the proton, neutron, and electron in kilograms. We also have it in what are called AMUs. This is atomic mass units. And then we have the charges here. And again, those charges listed are what we would call relative charges, not the actual charges in coulombs. Now, we could add to this. I wanted to put one more skinny column right here and call it relative mass. The reason for this column will become apparent in a little bit. But one thing that we can notice, the difference between a proton and neutron, other than its charge, is that the neutron is just ever so slightly heavier. But it's ever so slightly heavier on the fourth significant figure, which means we're really talking about really, really fine differences in mass here. So if we were going to standardize the mass of the proton and neutron, we could say that they're basically equal to each other. They have a relative mass of, since we're standardizing, they have a relative mass of 1. And since they're so stinking close to each other in mass, we're going to ignore that slight difference in that fourth significant figure. Because chances are pretty good we're not going to notice that kind of a difference anyway. Well, if the mass of a proton and an electron, or excuse me, a proton and a neutron are 1, what do you suppose the relative mass of an electron would be? Yeah, it'd be 0. Remember, a proton is almost 2,000 times greater in mass than an electron. So if I wanted to put that into fractional terms, I could put 1/2000th. 1/2000th in decimal form is 0.0005. Which again, if we're just kind of rounding to terms that we can understand, that value there is practically nothing. Now, why go through all of this? Well, we're going to get to in a little bit here the idea of something called atomic mass and mass number. And when we talk about atomic mass and mass number, we really are focusing just on the nucleus of that atom. Because ultimately, when it comes to mass, the electrons don't matter. I've got to pick up nearly 2,000 of them to match up to one proton. There's no such thing as an atom with 2,000 electrons in it. In fact, there's no such thing as an atom with more than 118 electrons in it. So to go to that scale, it's inconsequential. There's no way we can get to a point where there are enough electrons in an atom that they actually make a difference in the mass. So we can ignore them. So we start to ask some really interesting questions now based off of this series of ideas that we've been covering. And one of those things that we need to ask is, well, what makes an element unique? What makes an element gold as opposed to silver or tin? And it comes down to that nucleus. And in particular, it comes down to the protons in that nucleus. The defining characteristic of an atom is its protons. The number of protons in an atom's nucleus dictates what that element is. And so we have a particular name for that piece of information that tells us the number of protons. We call it the atomic number. The atomic number is given symbolically by the letter Z. On your periodic tables, it is the number that is usually on the top or directly underneath the symbol if there's no number on top. So on the table here that we have in our classroom here, you can see that the atomic number is the number in the top right-hand corner of the table. Right. I've just given you a periodic table. I want you to hang on to this. This is your periodic table. We're going to be adding some different things to it throughout the course of today and on Friday. So think of this as kind of your personal homework guide, because a lot of the stuff that we're adding to is going to be stuff that is going to be really vital to know and really useful when you get to homework and other kinds of preparatory kinds of things. Can't use them on the quizzes, can't use them on tests, but get you started, give you some information to become familiar with. So on our periodic table, it's not the top right corner, it's the top center. That's your atomic number. Now, when it comes to the periodic table, a lot of how the periodic table is organized can be attributed to a lot of different individuals. Now, this gentleman here, the Russian physicist slash chemist, Dmitry Mendeleev, probably gets the most credit. And I'd say he gets the most credit because of those that were working on it, he probably did the most. And one of the things that he was able to do, and one of the reasons why he gained such notoriety, was he was able to establish that there was a pattern amongst the elements. Now, Mendeleev ultimately used atomic mass, the mass of an element, to organize his order and help to find patterns. It was later discovered that that was kind of it was kind of in error, but he didn't have knowledge of atomic number yet. Once we established the number of protons in a nucleus, we were able to take his model and make it just a little bit better by fixing a couple of the places where the elements seem to be out of order. But ultimately, what made Mendeleev's table so great was he was able to identify that there were clusters of atoms, clusters of elements that had similar properties. And when he arranged the elements in order from smallest to largest, he noticed that there was a repeating pattern that was being generated. Every every eighth element would have a set property that was unique, that was the same as the 1/8 before it or 8 after it. And another thing he was able to do was he was able to predict that, okay, right now, as it exists, I know of gallium, number 31. I know of arsenic, which is now number 33. The thing is, arsenic, according to what we know about chemistry, should be the next in line. So it should have properties similar to carbon and silicon. But arsenic doesn't have properties common to carbon and silicon. It has properties more similar to that of phosphorus. Light bulb. What if the reason why arsenic doesn't fit there is because arsenic's not supposed to be there? What if there's supposed to be another element in between that we just haven't discovered yet? And so what he was able to do is he was able to recognize that there were gaps in our knowledge. And all he was able to recognize gaps, he was able to predict what some of the properties would be for that theoretical element that hadn't been discovered yet. And surely enough, within a little bit of time, the element germanium gets discovered, and germanium has properties very similar to what he predicted it would be. So again, that's one of the reasons why he gets credited with a lot of this. He certainly didn't give us a perfect version of the periodic table, but he gave us a lot of things that were good. And he was able to predict some of the things that weren't there yet. And so that structure of similar properties and different kinds of information being grouped in similar kinds of ways ultimately influenced our construction of the modern periodic table. And so what I want you to do here is I'm going to be presenting some information that is present in a lot of different places here. What I want you to do is feel free to start writing on your table as I'm writing on my table to start to pull out some of these similarities and some of these overall ideas. So first thing that we should do, our periodic table is organized in two ways. We have the periods. So periods are rows. And we have groups. The groups are our columns in the periodic table. And we sometimes will refer to these columns as families. Why do we refer to them as families? Because ultimately these groups are the groups of elements that have similar kinds of properties. And so like a family has similar kinds of character traits or physical appearance traits, so do these elements in a given group. They have certain things that are characteristic of that group that are unique to that group. Now, from a numbering system perspective, periods are numbered 1 through 7 from the top to the bottom. Groups can be arranged in 2 different ways. And if you look at the table that I gave you, we use in this table what is called the IUPAC numbering system. The IUPAC numbering system just numbers things 1 to 18 from left to right. So IUPAC, IUPAC, International Union of Physics and Applied Chemistry. Just a straight numbering, straight across 1 through 18. There is a second numbering system. It's called the CAS numbering system. You will see it in your textbook. You'll see it in a couple of other places. I'm not going to use it terribly often, except for when it's really valuable for us to use it. But in the CAS numbering system, you have 2 different sets of groupings. You have A grouping, where we number things from 1A to 8A, and you have B grouping in the transition metals, 1B to 8B. Now, where it gets confusing in the CAS numbering system is a couple of places. First of all, in the CAS numbering system, instead of 1B being over here on the left and 10 and 8B being over here on the right, you can see that 1B actually starts in the middle of the table, and 2B is next to it, and 3B is way over here, and 8B is these 3 columns over here. Like I said, it gets a little bit confusing. That's one of the reasons why I don't use it very often. Now, there are some advantages to it, but there are advantages that you really don't see until you get into upper levels of chemistry. So we're not going to bother with most of them here. Like I said, we will use the CAS numbering system when it is convenient to us. And there will be a couple of places where it is convenient to us to use it. But for the most part, we'll just stick to the IUPAC system because it's a lot more straightforward. Couple of points of interest for us. So on your periodic table in mind, you will notice that there is this kind of a staggered staircase thing kind of going between the elements in the middle of this big block on the right. That is the dividing line between metals and non-metals. So on this side of the staircase, you have metals. On this side of the staircase, you have non-metals. And so if I were to shade this in, which I would not encourage you to do unless you have lots of colors to choose from. But you can see that all of this including these down here, those are all metals. And on this side, these are your nonmetals. Now, pretty big gap in terms of the number of metals versus nonmetals. There are far more metals than there are nonmetals. But what about these ones that I didn't shade in? These ones, which I'm going to highlight here in purple, these belong to a different group. These are what we would call metalloids. sometimes referred to as semi-metals. And in terms of like defining characteristics, I can give you some. So I won't elaborate over these. You can read these on your own. But the properties of metals tend to have they tend to be flexible. Metals tend to be shiny. They tend to be good conductors. And one thing in terms of chemical reactivity, we'll find that they are usually oxidized pretty easily, which means that they have a tendency to lose their electrons. Non-metals, on the other hand, are kind of the opposite. Instead of being flexible, they're super brittle. Instead of being shiny, they're kind of dullish usually. Whereas most metals are solids, non-metals can kind of fall in a bunch of different categories. They can be metal, they can be solids, they can be liquids, they can be gases. What I will tell you about the ones that are solids and liquids is that it doesn't take much to turn them into liquids and gases. They melt at relatively low temperatures, they boil at very low temperatures. They have a tendency to be less associated with themselves than other kinds of materials. Now, the metalloids, on the other hand, we tend to see metalloids kind of having mixed properties. So instead of being solid and brittle, they might be solid and shiny, but not terribly conductive as far as electricity goes. Or maybe they have a little bit of flexibility to them, but they're more like insulators than conductors. So of these, I would say the most well-known one is probably silicon. And that's because silicon, as a semi-metal, is also known for being kind of shiny, yet really brittle, but also has the capability of being a pretty good conductor of electricity if the conditions are right, which is why they're used in things like computers and in semiconductors and different kinds of materials chemistry. So that's the first thing that we can do with our periodic table. Periodic table uses instructions to separate the metals and the non-metals from each other. What are some other things that we can do? Well, one of the things that we can do is we can start to look at things from a perspective of position. So I made mention before the idea of transition metals. Transition metals are the elements that are found in the middle of the table. These are the ones that the CAS numbering system puts a B label on instead of an A label. The main group elements are the ones where the CAS numbering system has an A on it instead of a B. You can also think of it as, for whatever reason, when I started studying chemistry for the first time, I could imagine the periodic table as like a castle where you've got towers and parapets on the big sides, and you've got a moat around the castle on the bottom. The main group elements would be the towers. The transition metals would be kind of the walkways and the moat. Just an easy way visually to kind of separate those two from each other. One thing that is definitely known and we can bank on pretty well is that when it comes to predicting properties, there is a lot more consistency among the main group elements than there is among the transition metals. Transition metals have a lot less consistency their properties are a little bit less defined than the main group elements are. Speaking of, I want you to highlight 4 different main groups. So in group 1A, these are known as alkali metals. Alkali metals, AlKali. In group 2A, group 2, we have what are called the alkaline earth metals. These are also metallic. They have very similar properties to alkali metals, but generally to a lesser extreme. And I'll talk about the differences between those two in a minute. So if you've got those 2 groups highlighted, the alkali and the alkaline earth, flip over to the other side. On the non-metal side, we have group 7, group 17. Those are the halogens. And in group 8A, group 18, you have what are called the noble gases. Now, why focus on these 4 groups in particular? Well, because these 4 groups are the ones that have the most familial properties associated with them compared to all the other groups on the periodic table. And so I wanted to take a couple of minutes before we close out for today to talk about these 4 groups individually here. So if you're still copying down, what those are, that's okay, because we're going to talk about each of those groups individually here. So if you didn't catch how to spell halogen, for example, when we get to halogens, you'll have a chance to see it again. So the alkali metals, group 1 or group 1A, we're talking about the first column in the periodic table. These are highly reactive metals. Highly reactive. They burn vigorously in the air. They burn vigorously in water. They are so reactive that they generally do not exist as elements in the real world. We usually find them bonded to something else, usually oxygen. So if I'm looking for lithium deposits to make lithium ion batteries, I'm not going to find pure lithium out there somewhere. Chances are what I'm going to find is a whole bunch of lithium oxide, and I'm going to hope that I can take that lithium oxide and chemically convert it to elemental lithium to make whatever it is I'm trying to make. When they burn, it's a pretty vigorous reaction. Group 2, the alkaline earth metals. What we see in the alkaline earth metals is a very similar kind of description. They react with the air, they react with water. We generally don't find them in their natural pure elemental form. Now, the question you're asking yourself is, well, why don't we just consider them alkali metals? Well, there's one really big reason. The reactivity is not the same. While they do react with air, while they do react with water, they do so to a much lesser extent, much less quickly. So if you drop sodium into water, it'll immediately ignite and give you this big fireball. If you drop magnesium into water, it's going to take you several minutes to even notice that it's reacting in the first place. One of those things, you come back and you look at it 20 minutes later and go, oh yeah, there's a bubble there. This is an example of calcium in water. Calcium will bubble up in water, so you know it's reacting, but it's not going to catch on fire. In fact, it's just going to sink to the bottom and just generate a whole bunch of hydrogen bubbles. So do they react with the same stuff? Absolutely. Do they react in the same way? No. And that's why they're in separate columns. On the non-metallic side, halogens. You can almost think of halogens as kind of being similar to alkali metals. Not in terms of they react with air and water, but halogens are highly reactive. So reactive, in fact, that if they don't have something to react with, they will react with themselves to form molecules. You might have heard it mentioned that there are certain non-metallic substances that don't exist as atoms. They form diatomic molecules. Every single one of the halogens fit into that category. So fluorine doesn't exist as F, it exists as F2. Bromine doesn't exist as Br, it exists as Br2. Now, there are other elements that do that as well. Oxygen, nitrogen are prime examples of that also. But it's common all up and down the halogen group. They're highly reactive. And so even though we don't associate the reaction with water or with air, we understand that they are reactive enough that if they don't have something to react with, they will react with themselves and form molecules rather than stay atoms. The last group that we're going to take a look at, the noble gases, group 18, group 8A, these are the unreactive gases. And so that particular group on the periodic table is unique in the sense that it is the only group on the periodic table where none of its elements form compounds. We might have an example here or there of an inert metal or an inert element, but they're kind of unusual cases. So gold and platinum, for example, they don't react very much with anything. But can we get them to react? Absolutely. It just takes the right kinds of circumstances. There are no compounds of neon. There are no compounds of argon. There are a few compounds of xenon where we've basically forced it to pair up with fluorine because fluorine's so reactive and it'll take on anything. But those compounds that are made are highly unstable. Simple drop of water, they completely dissipate back into xenon and fluorine. On Friday, we'll talk about these last couple of concepts here in chapter 4. We'll talk about ions. We'll talk about some of the other information on the periodic table, including what's that number on the bottom all about? Because that number is an atomic mass, and it's got a little bit more layering to it in terms of what we actually do and how we calculate it. So we're going to need to take a deeper dive on that, and we'll do so on Friday. Before you leave, hit me with one of these. And once you do so, have a great afternoon. I'll see you on Friday.